Hey folks, so in this video lesson we're going to go ahead and take a look at the moon, right? We're going to look at the motion of the moon, we're going to look at lunar phases, and we're going to look at eclipses as we continue to build on our model of the sun, moon, and earth system. So if we start talking about the motion of the moon, right, just a couple things that we can notice, a couple things that we can observe, and it's all about this idea of observation, right? So we've got this orbital period of 27 days. Right, so it takes 27 days for the moon to go around the earth, but the lunar phases, so our waxing crescent, waning crescent, your gibbous, your full moon, your new moon, all that stuff, that's actually going to take 29 and a half days to complete. So even though the moon goes around the earth, it takes 27 days to do so, it takes 29 and a half days to go through those phases. Right, and that discrepancy, because you would think, oh, the period and the lunar phases should line up. We got to remember, right, the Earth is still in orbit, right? The Earth itself is still rotating along its axis. So as the moon, rotates and spins, the Earth itself is continuing to rotate as well. So you have this dynamic system of a rotating Earth, a rotating moon that is in orbit, right? So we get this spinning body with a spinning body, and the moon is going around the Earth, which is still in motion, right? And again, in order to complete its orbit, the moon has to continue traveling as well, right? So again, it's this big dynamic system that we see. So because of this, the moon ends up in slightly different locations each time around, which is why we get that 29 and a half days, because the phases are also dependent on the location of the sun in all of this as well, because that's where the moon is going to get that light to reflect back to the Earth. Now, the synchronous rotation is why we're going to get the same side of the moon to face the Earth. So when you look up right, you're always going to see the same face of the moon. And that's because as the moon rotates, it rotates at the same rate that it's in orbit, which is what's going to keep that same face towards it. If the moon were to rotate faster, right, because you picture on Earth, a day is that 24 hours it takes to spin on our axis. Well, for the moon, the rate that it's going to spin on its axis is going to match the rate that it's orbiting around the planet, right? So based on that information, right, we're never going to see the far side of the moon, right? So we're always going to see the near side. We never see the far side. No such thing as the dark side. Based on Pink Floyd's Dark Side of the Moon, right? That whole song. There are times when we do see the dark side of the moon, right? And that's going to be the full moon, because when the full moon is there, all the light's hitting it. Well, as it then rotates away, right, we are going to see the dark side of the moon, right? Because then that's going to be our new moon, right? The new moon is dark. At some point, right, based on the gravitational pull between the two bodies, right, the moon and the Earth are eventually going to tidally lock with each other. Now, that's going to be billions of years from now, so we're all going to be long gone. But basically, the moon and the Earth are only going to show the same face to each other, right? So as the Earth orbits and the moon orbits, we're going to see the same faces looking at each other the entire time, which would mean there are going to be places on Earth that aren't going to have the moon anymore, right? They're just not. It's not going to show up, right? It's going to be in one location, and if you're not in the right spot on the Earth, you're not going to see the moon. So here we see our lunar phases, and an important thing to look at here, right? So we've got the sun coming from the right. Here we're showing what the phases are along the outside. The inside is showing how the light is hitting it, because half of the moon is going to be receiving light at any given point in time, but it's where the moon is with respect to the Earth and the sun that is then going to give us those different phases. So if we start here at A, right, that's going to be our new moon. So notice that the far side of the moon is bright, the near side of the moon is dark. That's our new moon, right? That's the side that's not receiving light. And as the Earth continues to rotate and as the moon goes around it, note the counterclockwise direction that the moon is going around the Earth, right? We see South America and North America here, with Africa over on this side. So technically, right, as this moves, the moon going counterclockwise around the Earth from above is actually going to be going from west to east in its orbit, and it's going to match the direction that the Earth rotates. The Earth rotates from west to east, and the moon orbits the Earth from west to east as well. So as we continue to move, right, we're going to get the waxing crescent to the first quarter to the waxing gibbous. So we're going to see the moon get brighter as it goes, right? So waxing means we're going to get brighter, and it's going to get brighter from the right side to the left side, right? So the darkness is going to fade away as it waxes. Then we get to our full moon. Full moon, if we look here, the full moon is on the opposite side of the earth as the sun, right? All the sunlight is going to hit this part of the moon right here. So now the dark side is the far side. The side that we see is then lit up. Then the moon continues in its orbital path, and now we see waning and waning with the third quarter. So we get brighter as it waxes from right to left, and if you look at how it gets darker as well, right, we're getting darker from right to left, right? So the light shows up, and then the light disappears. So the last part to get bright on the moon as it waxes is the last part to fade away as it wanes. So here we have two pictures. Here we have a picture of a waxing gibbous and a picture of a waning crescent. Again, notice how that waxing gibbous almost full, and that waning crescent, we see that nice stereotypical sliver appearance of the moon there. All right, so as it orbits, we're going to take a look at all of these terms here. But again, it's going to appear to orbit eastward against the backdrop. So it goes from west to east, but it moves so slowly that this becomes a really hard thing to notice, right? We still kind of get that rise in the east and sets in the west thing, but in the grand scheme of its motion, it slowly creeps eastward as it moves. Now, we get our terms that we're going to use to describe the phases, right? So new, it would be a dark, right? That'd be a darkness, all dark, right? Dark moon, new moon. Crescent is going to be this sliver here. A quarter would be half. A gibbous is going to be a good-sized chunk of the moon. Full moon would be the entire lunar surface. Waxing means it gets bigger. Waning means it gets smaller. And when it waxes, we're going to gain more light on the moon. And as it wanes, we're going to lose that light on the moon. And that's going to go from right to left. So when it waxes, it's going to go from the right side to the left side as it gets brighter. And as it wanes, it's going to go from the right side to the left side as it loses light. So here again, just looking at the lunar phases, new moon, right? Still there. I mean, you can still kind of see it. We just don't get that direct sunlight to be able to reflect off the surface of the moon. We wax on, we get the full moon, and then it wanes away. So the sun in this diagram would be off to the right-hand side as well. Note the counterclockwise motion of the moon around the earth, which is going to be from west to east as we would see it from overhead. Now, this is a pretty good diagram here because we're showing the ecliptic plane. So we've got the earth tilted 23.5 degrees on its axis. So that 23.5 degrees is going to be represented with respect to the ecliptic plane, so the path that the sun is going to travel. So here we have our north and south pole as it would be magnetic. Here we have the ecliptic north and the ecliptic south pole, which are not going to be our geographic north and south as we would perceive them on a map. So notice the rotation here of the earth rotating from east to west. Right, so we're going to, from west to east, west to east on that rotation here. The moon is going to rotate in the same direction, right? So the moon is also going to rotate from west to east. We're going to be traveling counterclockwise around the earth, but at a 5-degree tilt with respect to that ecliptic plane, right? And that does become substantial later on here. So here's the ecliptic plane, and here we have our 5-degree difference between them. So now, as we go and we look through some of the eclipses that we can get here, this is where we really see the importance of that 5 degrees, but also how that path is going to dictate what we see with our eclipse. Right? So here we have our solar eclipse, here we have our lunar eclipse, and we get 2 different types, which we're going to cover in depth right now. So our 2 primary types, we have a solar eclipse and we have a lunar eclipse. The solar eclipse is when the moon is between the earth and the sun, and lunar is when the earth is between the sun and the moon. The object that is being blocked is the name of the eclipse. So a solar eclipse means that the sun is being blocked, and a lunar eclipse means that the moon is being blocked. We have two primary parts we look at in an eclipse. We have the umbra and the penumbra. So the umbra is going to be the dark part, and that's going to be cone-shaped. The penumbra is going to be a diffuse region where it's still a shadow, but it's not nearly as dramatic as the umbra itself. So the umbra is going to be the really dark spot. The penumbra is going to be a much broader region that's still going to be a shadow, but not a huge shadow. Okay, so this first video here, I actually do have linked in the Schoology video lesson itself. We're not going to take the time to watch it on here, so please make sure that you watch that when you go through to answer the questions. It's a short clip, but it does a really good job with the visuals. So we're going to move on here, right? Looking at the lunar eclipse. So here we got the sun, Earth, and moon, right? Note that order: sun, Earth, moon. Lunar eclipse means that Luna, the moon, is being blocked by the Earth's shadow. So as the moon orbits around, again, noting that clockwise or that counterclockwise motion here, the moon is going to enter the umbra of the Earth. So look at the cone shape that we get for the umbra here. The moon is going to pass through there, and it is going to appear that dark, ruddy red color, because as the light passes through Earth's atmosphere, that blue light is going to bend far less than the red light is. That red light is going to refract inward, creating the cone, thus the umbra making that appear very red. So whether it's in the umbra or the penumbra, whenever we have some form of a lunar eclipse, it is either going to be passing through the penumbra of the Earth or the umbra of the Earth, and it's going to last a pretty substantial amount of time in comparison to a solar eclipse. So again, here's your look at it. Light hits the Earth, right? So we get all sorts of different light coming at the Earth. It's going to hit it. We're going to get that red light to bend quite a bit, and the moon would pass through it, thus creating our different colors. So you can see how wide the penumbra is in comparison to the umbra. Remember, the penumbra, we're still going to get some shadow there. So if the moon passes through it, you'll be able to tell. It's just not going to be nearly as dramatic as when we get a total lunar eclipse, as that light becomes red and the moon passes through the umbra and has that red appearance. Solar eclipse here, same deal. I've linked both of these videos in with the video lesson itself, so we're not going to do it here, but please watch each of these videos with the video. So we're going to pass by those. So our solar eclipse, right, what we see here. Now we have the sun, the moon, and the Earth in that order. Light from the sun gets to the moon. So as that light reflects here, notice that the far side of the moon is going to be illuminated. The near side of the moon is going to be dark. So this will only happen during a new moon. And for a lunar eclipse, should have said this one, that will only happen during a full moon, because the moon is on the opposite side of the Earth from the sun. So we get a new moon for a solar eclipse, a full moon for a lunar eclipse. So light strikes the moon. Same deal, we get that shadow, so we still get the cone-shaped umbra, and then we get the much broader sweeping penumbra that we're going to get right here. Now, how this one ends up appearing on Earth, it is a small area based on how far away the moon is from the Earth. If the moon were closer, the umbra would cover a larger area. If the moon were further away, eventually there would be no umbra hitting the Earth itself, and we wouldn't get that same total solar eclipse appearance that we do. So when you're in totality, as it's called, the total darkness, you're in the umbra of the moon. And if you're anywhere else, you're in the penumbra, where you can see the moon crossing over a good portion, but not all of the sun based on your location. Right, so looking again at how this works, this would be totality in the umbra. This would be a partial solar eclipse if you're in the penumbra. And these have to be in the exact same line. That's the important piece here, right? If the moon is slightly offset from the Earth or slightly offset from the sun, we're not going to get totality. Which kind of brings you, right? Why don't we get more eclipses? Why don't they happen more often? And the truth is they actually happen quite a bit. You can look up plenty of maps that show, yep, here's a solar eclipse, and here's a lunar eclipse, and here's a solar, and here's a solar, right? We get this idea that solar eclipses don't happen a lot. They happen more often than you'd think, right? Every couple of years or so, we're going to get a total solar eclipse. It's just where it shows up, right? When they show up in the U.S., like the one did in 2017, they don't happen very often in the U.S. But in the grand scheme of the globe, they happen a fair amount. A lot of them are going to be over water. Still not as often as you would think, though, right? Because your train of thought would be, well, every time that the moon passes through, we should be getting an eclipse. But remember that 5 degree of orbital incline. That's what causes the lack of eclipses compared to what we would think it would be. And that 5 degrees of incline, we still don't know why that is. We still don't know why the moon's orbit is offset at 5 degrees the way that it is. But because of that, we don't get nearly as many as we would think. Now, let's say that the moon's orbit was not offset by 5 degrees. If it was on the exact same path as the ecliptic, well, that would mean that every single time we had a new moon, we would have a solar eclipse. And every time we had a full moon, we would have a lunar eclipse, right? And that's because that light that would be hitting the moon or coming off of the earth, depending on your orientation, we'd get that eclipse every time because it would pass perfectly in between the earth and the sun, or it'd be perfectly on the other side of the earth in comparison to the sun, right? So we'd constantly be getting those. So we would see these frequently, right? Every single time that in that 29 and a half days, we would get a lunar eclipse and we would get a solar eclipse, right? Because all of them would have to be on the same line. And if they're not on the same line, we're not going to get either a total eclipse or we're not going to get an eclipse at all. So this last idea here, right, with why they don't happen so often, it comes down to this thing called the line of nodes. So if you look here, right, we have the moon's orbital path right here. We have the ecliptic plane right here with the Earth in the middle. So the ecliptic plane, as we see, right, pretty flat. Here we have the moon on its orbital path. So at these nodes right here, if you look, there are these very specific locations where the moon's orbital path lines up with the ecliptic plane, so the motion of the sun in the Earth's sky. So when the moon's orbital plane intersects with the ecliptic plane, that is when we can have an eclipse occur, because we're going to be on the same line, and that is known as the line of nodes, and that intersecting point is the node where these two planes come together. But here's the issue. If the moon crosses the line of nodes right here, and the sun happens to be to the right, we're not going to get any sort of an eclipse, right? We'd be looking at a third quarter moon, which is not a new moon, and it's not a full moon, so we wouldn't be able to have it. If the sun is to the left side and we're right here, well, now we'd be looking at a first quarter moon, and we're not going to get an eclipse. So the only way this happens is when the moon is at this line of nodes and the sun is somewhere along that line as well. If we're on this node here and the sun is towards the bottom of the slide, we'd have a new moon, which would then tell us that we would be having a solar eclipse. If the moon is at the same node and the sun is on the other side, we'd have a full moon, which would give us a lunar eclipse. All right, so the location of the moon, the sun, and the earth are very important when it comes down to what type of eclipse we're going to have. So what we can learn here today, right, is that not only do we have the phases of the moon, but the phases of the moon are dictated by how the moon orbits, right, the rotation of the moon, its eastward motion, right, it goes west to east based on its rotation, based on the rotation of the earth as well, right, we get that sort of offset between the orbital period and the lunar phases, and all of that ends up being significant to how we get our eclipses. Thanks, guys.